So yes, there is a lot of all these different things for every A-level student. And actually, I think that often the 6-mark questions or extended response, that's what they're properly called, okay? Because they don't have to be 6 marks. It could be 7, 8, 9, more. Yeah, they can just be long. If you are not very confident at chemistry, the likelihood is you might just completely leave them. If you're very confident, the likelihood is that you spend too long on them, and not as long as you would spend on separate questions that may be added up to the same marks. So we need to get a little bit more efficient. And there's definitely a case of not knowing how to structure your answer. So we're going to look at some tips and strategies. We're also going to look at a few specific examples, not many, because, they're extended, right? So we don't have a huge amount of time, and I'm trying not to go past an hour because that's crazy time. And at the end, I'm going to give you some just info on some useful resources for A-level students. Some of those are free, and some of them are just like really heavily discounted over half term. So it's a good time to be thinking about your revision, actually, because a lot of people aren't. So what is actually an extended response question? We kind of need to know that. This is clearly exam board speak. This is not from me or from any student that I know. No student would answer the question like this. They are in pretty much every subject because they have to be. Okay, like they didn't used to be, and then the government was like, hey, you can't just do science with equations, you've got to write stuff. However, I only want to look at this because of some key words. Sustained line of reasoning isn't as important as you might think in chemistry, and we're not building an argument. We're not writing a thesis or anything. Coherent, yeah, okay. Coherent is important. I need to be able to understand what the person is writing. But the most important parts of that are the last 3 words or the last 3 descriptions that are given. Relevant is a big problem. That is where students are losing marks, not through no content, but through irrelevant content, through just throwing out everything you can think of on a particular topic instead of reading there's loads of clues in the question usually. Substantiated, I had to Google that. I thought I was quite good at English, but I had to check. Is, based on evidence, like, you've actually, and that's another thing that students don't do. They don't actually look at the information provided and link their answer to that information in the question. And logically structured, we know that that's where some of the marks are coming from. Now, extended response doesn't have to be written. It can be a calculation as well. Many 6, 7, 8 mark questions are calculations. They're still called extended response because they still have the same thing in common. You have to structure your answer. You have to be logical about it, about the order that you do things in a calculation. Otherwise, just be nonsense. And you have to be clear what it is you're doing at each step in, say, a big titration. We are not going to go through the calculations once today because that would be a whole separate lesson, but I will point you in the direction of some useful stuff. So it used to be called quality of written communication, and luckily it's not called that anymore. But people worry about, how should I write it? Am I expected to be writing this like an essay? So when it comes to chemistry, structure is about linking ideas together. It's not about your paragraph or sentence structure. Like, we obviously need to be able to understand what the subject of the sentence is. We want to avoid just saying it or they or leaving out the subject. So there needs to be some sort of structure that is understandable, but it's not about an essay structure. It is about linking things, i.e., if you are talking about the bonding, are you linking it to the numbers that you've been given in a table related to that substance? That kind of thing. So structure, linking ideas, really, really important. Spelling, is it important? Well, yes, because if I can't tell whether you've written alkane or alkene, that is a problem. So some words, okay, if you get the wrong form of there, it's going to be painful for the person marking it, but it's not going to necessarily impact on the chemistry. So spelling is important for keywords and for sort of readability, like so that we can actually know what's going on without really thinking so hard about it. And then there's this thing about irrelevant content, which I mentioned. So you're not marked down if the question asks about conductivity and you talk about melting point. You won't lose any marks if you write about the correct things. You know, if you start talking about bonding and relating it to other properties, solubility, melting point, that kind of thing, you don't lose marks. For the chemistry, unless you write something that contradicts your chemistry, which is easy to do. The more you write, the more likely you are to write something wrong. And if it's really wrong, you start to lose the chemistry marks. But you will also lose your logic and structure marks if you're just throwing out everything. And usually the marks are leveled and they are broken down into the actual chemistry. So there will be, depending on your exam board, on the mark scheme, there is usually a box of stuff that says indicative marking points or suggested marking points. And that's like the list that you want to look at, because the other point is going to be absolutely impossible for you to determine. So if you're looking at a mark scheme and you're trying to mark your own level of response, number one, it is super hard. I've been doing this for 20 years. I've been marking exams for 20 years as well. I still find it quite challenging marking level of response. So if you're doing it yourself, don't try to sort of interpret where you are in the logical order and sequence. Just look for how many points did I get out of all of those chemistry points and what did I miss? That is the main thing to get out of a mark scheme. Okay. And then finally, bullet points. Everybody asks about bullet points. Yes, you can use them. I'm a big fan, obviously. But if they're not in the right order, then you're going to lose the previous marks. Okay. So if they're not clearly linked together, if they're just your excuse for trying to tidy up your thoughts, but they're not really tidied up, you know how when you have a big mess, you put it in a box and put the lid on it, and now it looks tidy, but it's not if you open the box. So that's my way of tidying. Don't try to organize your thoughts simply by putting a bullet point next to it does not make it logical. What makes it logical is if the thing that you just wrote then follows on to the thing that you next write, if they are linked. You can plan. So you may find that you've got loads of space, and you should have loads of space because you shouldn't need more than about 8 lines to answer a 6 marker most of the time, unless your writing's huge. So you could use half the page to plan your answer, cross it out, and then write your, if you are a very messy thinker, do it like that. And the reason I say cross it out is because otherwise the examiner is going to mark the whole thing, even if it's just your plan, because they don't know and they have to mark things that are not crossed out. If you cross it out and then run out of time and it's still readable, they'll still mark it. That's how much we have to check what you write, is even if you cross through it. I did forget to say as well, by the way, you do use the chat all the way through if you've got a specific question about any of this, but I'm trying to talk about just general tips. So, strategies. We want to avoid panicking. We want to get some structure. We want to know how to practice and revise for these, because that is the best way to avoid panicking about them. And we want to avoid worrying about the total marks and just think about maximizing your marks, i.e., not many people are going to get 6. Not many A-star students are going to get full marks in every level of response question. That's not what they're, they are for distinguishing between different levels. So what you want to think about is, how do I just get myself to that next level? How do I just get myself that next 1 mark? And then maybe next time I can get myself that next 1 mark even more. rather than thinking, how do I get 6 marks? It's nice, but it's not essential. Okay. One way to avoid panicking is to obviously look at all of the stuff that's given to you in the question. Don't panic if you're either in year 12 or just haven't done transition metals. I'm not going to go through the answers to this question. It's not on every syllabus anyway. It was just a nice example of, this is 3 questions, right? So when you first read it, it has the word discuss, which is a bit meaningless. It sounds like it's going to be an essay, the role of iron as a heterogeneous catalyst. But then it says, tell me what heterogeneous catalysts mean. Tell me how iron acts as a heterogeneous catalyst. And then the factors that affect the efficiency and lifetime of the catalyst. So really, that is like a 1-mark question to start with. 1A, part I, what is a heterogeneous catalyst? Different state to the reactants. Done. Then maybe that's a 3 or 4-mark question sandwiched in the middle. Probably a 3-mark question. How it works, and if you do that on your syllabus, you got some steps that you could follow. That's quite an easy question, how a heterogeneous catalyst works. Absorbs on the surface, bonds weaken and break, new products form, and then they desorb from the surface. It's actually just something you can step through. And then the last bit is maybe the harder bit, the factors that affect the efficiency. Whack a bit of surface area in there because that's biology and it always works. So actually that's a 1-mark question, a 3-mark question, and a 2-mark question at the end. And most chemistry questions are like that. They really are, because examiners are lazy and they don't really want to mark big long essays. Well, not lazy, we just don't get paid very much. And chemists would rather have everything done in equations and diagrams and things and not have to plow through loads and loads of your text. So that means that the question is usually really clear exactly what it wants you to talk about. And you can normally even guess how many marks there are for each one. Some of them are even more obvious. So, I mean, it's not really an extended response question. That is 2 shapes of molecules questions about slightly different molecules. So, like, you get marks for drawing it, you get marks for naming the shape, you get marks for stating the bond angle. At the moment, all you've done is a series of relatively easy 1-marker questions. And the last bit is describing how you get to those shapes, which is the same every time. So there are some things that you can practice lots of. There are areas that come up time and again. Shapes of molecules is one of them. Make sure you know how to describe shapes of molecules. In fact, I've got a long answer example on YouTube where you can actually step through it. Then bonding and structure is the other really big area, and periodic table, periodicity, ionization energy, basically all those trends, that kind of stuff is really, really big. And then the other area that is long for written questions tends to be your, sorry, I'm having an absolute mental freeze, practical work, that was it, practical procedures as well. And most practical procedures are standard procedures. So that should be oh, thank goodness, I got how to make a standard solution or how to do recrystallization, because they are standard procedures. So you just write them down, you just learn them. We'll talk about a little bit about how a little bit later on. How we learn them is another question. Okay, so looking at examples, I wanted to use a couple of bonding and structure examples because they are really common, and talk about how we keep it relevant, because actually this is like a really specific question, and we want to try and get 6 marks out of it. So we look for the clues in the question: magnesium and silicon, elements. Elements can only be metals or non-metals. And if they're both giant, then there can only be giant metallic or giant covalent. That's your only options. And it's pretty obvious which one is giant metallic. So It says describe the bonding in magnesium and silicon. Include the names of the particles and describe the forces. So they're really spelling it out. Like, please, could you put these things in your answer? But a lot of students skip over it. Don't slow themselves down. You don't need to answer a 6-mark question in 6 minutes. You can take 10, because some other question's just going to be a really quick tick of a box. It's not going to take as long, or just a one-word answer. It's not going to take you a whole minute. Okay, structuring. How I'd structure it, definitely just, it's 2 questions, right? It's a question about magnesium. It's a question about silicon. It's just describe. There's no explanations. There's no linking it to any properties whatsoever. So if anything, it's almost just a test of what your bonding is. So you would just say that magnesium is giant metallic. You would say what that actually is, which is a lattice of metal cations, naming the particles, surrounded by, actually, no. Yeah, no, I'll say surrounded by delocalized electrons. So I've named the particles. And then we can say it has the strong electrostatic force between them. That's it. I have nothing else to say about magnesium. I've just said what it is. Also, if you're not so good at it, label a diagram. Silicon, I wouldn't dream of trying to draw a diagram for silicon, because it's going to have a similar structure to diamond, which is very difficult. But if it's a non-metal and it's giant, then it must be giant covalent. This time we've got to describe covalent bonding, which is rare, and that's why I included it, because normally when we talk about covalent things, we just say, oh, the covalent bonds are strong and the intermolecular forces are weak, and then we just brush over the rest of it. Giant covalent, though, I need to actually talk really clearly about the forces between particles. So it's the electrostatic attractions, again, between shared electrons and the nuclei of each atom. So I'm writing on a bit of a slope and my handwriting's gone a bit wrong. So I would also probably add in there that silicon would be bonded to 4 other silicon atoms because it's in group 4. But other than that, there's nothing else to say. I don't need to talk about melting point, boiling point, conductivity, nothing. It's really easy to keep this logical by splitting up the substances. So there are hundreds of examples of bonding in structure 6 markers. I would always recommend that you talk separately about each substance. Don't try to talk about melting point and then talk about conductivity and keep going back and forwards between 2 different substances, because you're going to at some point say they or it or something is going to contradict. So again, treat it like 2 separate questions. What type of bonding is there in magnesium and what type of bonding is there in silicon? All about describe, no need to explain anything. Conductivity, again, that's quite niche, that's quite specific, just the electrical conductivity. But again, it's sodium oxide and sodium. So again, you split it up. You talk only about sodium, which is exactly the same as what I just said for magnesium. Electrostatic attractions between positively charged cations and delocalized electrons, and then we link the delocalized electrons to the conductivity, which is just that delocalized electrons can move and carry charge. The other thing I was going to say is when you have a describe and explain, although I'm saying split up your answers. So I would start with sodium just because metallic is easier to talk about. I would move on to sodium oxide. Describe first, then explain. Always, or state, then explain. It does depend on the wording. Sometimes it will say state and explain, but we can say it conducts as both solid and molten. The reason I say describe before you explain is because you won't get into sort of the middle level of this question if you don't state first what the conductivity is, because you won't be able to get the marks, no matter how good your chemistry is after that, for linking conductivity with the structure. And what happens is we can get so tied down in explaining stuff that we forget to just state the obvious. Happens a lot with ionization energy questions. Now, ionization energies describe and explain the trend in first ionization energies down group 2. You go straight into shells, atomic radius, shielding. You're all getting involved. You forget to say what actually happens to it as you go down the group. So always get the obvious, most obvious points in that you can. So I would, even before I went on to the rest of it, say sodium oxide conducts only when molten. And in this case, I've got to talk about the structure. So ionic lattice. I did not write that down for sodium. You would, because we just wrote it down for magnesium, I didn't really want to write lattice of cations and delocalized electrons again. So only when molten, it's an ionic lattice structure. Strong electrostatic attractions. You can see that there are lots of words and terms that we can reuse between oppositely charged ions. As a solid, the ions are fixed in place. So always compare solid and liquid, or solid and molten. Molten just means melted, hot liquid. So they cannot move and carry charge. And then as a liquid, the ions can move and carry charge. That's it. So it's all just about what is there that is charged, that can move through the structure in the and relate it to the two different states. No point talking about anything else, melting points or anything else really, or other different things. So bonding and structure, the main issue is they're not actually that hard, the questions. It is just keeping it relevant and making sure they are linked. Okay. A few people asked about, you definitely get these longer questions about qualitative analysis, but this is a little bit of qualitative and quantitative. So qualitative analysis just means testing for stuff, but like not titration, which is testing concentration or amounts, but testing, just for the presence of certain things. So my tips are really, you have to revise this to answer this. You can't just go at it and guess. You cannot bring out ions tests unless you drill them, okay? Which is, what my dance teacher says about stuff. You have to drill these really boring things in order to be able to put them together and do the good stuff. You have to know what bubbles means. It always means the same thing. So I could look at bubbles and immediately know there's a carbonate ion. It didn't really matter what I added, to be honest, because the only reaction you do in A-level chemistry that makes bubbles is acid and carbonate, or acid and metal, but that's pretty, we're not testing for a metal, we're testing for ions. So generally, that's it. Doesn't matter what acid. So they've said add HNO3, which might throw some people because you might learn the test for carbonate as add HCl. But it's an acid, doesn't matter. And you might also learn that you're supposed to use HCl with barium chloride. Again, it doesn't matter. The acid just gets rid of the carbonate ions or whatever might be in there, like hydroxide. You also need to know and link what you add with what you see. So don't just learn white precipitate is this, because there's more than one. Lots of things are going to give you white precipitates. Spoiler alert. Most things in chemistry are white, except some transition metals compounds. So you just need to know which things pop up. and when. So in this question, it tells me that B contains carbonate and C contains sulfate. And if again, this is about knowing the charges on the ions. If you don't know the charges on the ions, you're going to mess up the next bit because they're both 2 minuses and this is a group 1 compound. They are both going to have the formula X2CO3 and X2SO4. So we can use those formulae and the fact that they are both about 140 as their MR. And then you just do a bit of maths. You add up CO3, you take it away from 140, and it turns out that it gets you a mass of 80. You divide that by 2 because it's X2, gets you 40, which is not calcium because they said it's about 140. It didn't say exactly. So the mass of X in this case is about 40. And when I do the same maths, stop me if you want me to go over the maths. I just didn't want to labour that bit because it's actually quite an easy calculation. The mass of the X in this one is about 22. So we're not going to look all over the periodic table for something that weighs exactly 40 because we could be coming up with potassium, calcium, or argon. We're only going to look in group 1. So that's going to be potassium. And then the other one is going to be sodium. So it's not exactly 22, but they said it's not exactly 140. So we're just estimating. Don't forget, therefore, to actually answer the question, B is K2SO4 and C is Na2SO4. If you are asked to, just look for those words, identify the formula, name it, different instructions. Identify the ion. That is a common question. It's not normally in a 6 marker, but that is a common question where people often just write slightly the wrong thing. Okay, or so they're not reading whether they should be doing ion, formula, or the whole name of something. So the other place where why is B not a carbonate? Did I not say B is a carbonate? Oh, so because B is a whole compound. And actually, that's a really good point when I talk about the practical stuff as well. So it says B and C right at the start are ionic compounds. It does not say they are solutions containing ions. It says they are whole ionic compounds containing group 1 and an anion. So you know that they're in group 1. You know that B contains carbonate. So it's a group 1 carbonate. And then we did the maths. Taking away the CO3 from 140 gives us 80 divided by 2 because it's X2CO3. Same with C. So C is a group 1 sulfate of some description. We know it contains sulfate. So we know the general formula will be X2SO4. We do the same thing, add up S and 4 O's, take it away from 140. We get 44, we divide it by 2. That's where the masses of 22 and 40 come from. But that's also a really important point for practical. So you get a lot of questions, organic chemistry in particular, where you have to describe, it'll say, you know, identify the reagents and conditions to get to this point. So words are important. Identify by name just means name it. Identify the structure of an organic substance means that you can draw it really however you like. If it says give the reagents, then a reagent is a bottle of something that I could ask a technician to get me from their cupboard or make up. So hydroxide isn't a reagent. Sodium hydroxide solution is a reagent. You see the difference. Dichromate, there you go, is not a reagent. Potassium dichromate, acidified potassium dichromate, that's something I could ask for. So you don't have to always name absolutely everything that's in there. And some reagents need a little bit extra. So if I went to a technician and said, can I have some sulfuric acid, please? Their first question would be, well, do you want like concentrated sulfuric acid or just dilute sulfuric acid? Do you need like a specific concentration? So therefore, try and be really, really clear. In this question, like you could get questions about how to test for ions, and you need to be clear that you're adding solutions of things. So acids are all solutions. Acids don't come in anything except solutions. But things like barium chloride, sodium hydroxide for your transition metal tests, that kind of thing, silver nitrate, those are ionic compounds. They come as solids. So you should state that you're adding a solution. When you're coming to practical details, it's important whether something is a solid or a solution. It's going to get a completely different kind of result happening. Which brings me beautifully onto a practical question, this time using a solid and making a solution and determining the enthalpy of solution. So if you're in year 12, you probably haven't done enthalpy of solution, but you could probably guess what it is. You take a solid, you want to measure the enthalpy change when you dissolve it. There you go. So again, it looks like there could be a lot of info. So when you get a practical question, it's quite rare in chemistry that they will ask you a 6-mark question to do like a really detailed plan. There's kind of 2 types. There is the describe this practical procedure that you should know really well, like making a standard solution, for example, or finding enthalpy of combustion. There are things that are core practicals or PAGs, however you want to call them, CPACs, depending like what exam board you have. They've all got different names. They're all the same thing. They are practicals that you can be examined on. That's why they're called those core practicals. Those, make sure that you actually know how to do them. This is a standard enthalpy change experiment. And so therefore there should be always things that we should always do. And the main thing for most experiments is tell me what you're going to measure and how. And in this question, we're then going to say how to use those numbers. So that's most chemical practicals. Most chemical practicals are either what you measure or what do you add, and then how do you do it. So in this case, we're trying to come to a number. So if it's a titration, enthalpy change, get focused on what measurements do I need to take. And the best way actually is usually to work back from the calculation and go, well, what is my calculation in? Enthalpy changes are in kilojoules per mole. So I need to make sure that I take measurements that get me those answers, kilojoules and moles. So if I need to know the moles of magnesium chloride, the reason it says about is because of how you weigh it. So I always remember this practical, and it had some instructions like real start of year 12, and the instructions said weigh accurately about 0.500 grams. And the students were just like heads blowing up. Like, what do you mean approximately 0.500 grams? Like, because 0.500 doesn't sound very approximate. It sounds massively like precise, that number. What they mean is they want somewhere between, I think they changed the instructions in the future years because it was too confusing. They want somewhere between, in this case, 0.78 grams, say, and 0.82. Like, it's not that important. What is important is that you know the number really accurately. So you don't just write down 0.8. You write down 0.803, for example. But it doesn't matter if you go over because you're going to do kilojoules per mole. And kilojoules per mole, like, you're going to know how many moles you've got from the mass. So when you weigh something out, there's actually more steps than you ever believe. You're going to weigh the empty like, or put the empty weighing boat on the balance. But weighing boat is the word for it. There's little plastic things, they're just called weighing boats. You would add about 0.8 grams. You would record the mass of both the things, okay, the weighing boat and the solid. Then, after you've done the next bit, which would involve a polystyrene cup, tipping the solid in, stirring it, and doing all of that, you go back and weigh that empty weighing boat again. And then that tells you exactly how much solid went into your solution. It's the same for making a standard solution. It's called weighing by difference. It's simply this idea of you weigh the container with the solid in it, you tip it out directly into whatever you're reacting it into, and then you reweigh it so that you know if there was any bits left on the weighing boat that they weren't added, and therefore you have a more accurate mass than just assuming that your 0.8 grams all ended up where it was supposed to go. So you weigh by difference, you do that bit. In this case, I would talk about using a polystyrene cup. I would talk about measurements. So in this one, we have to use Q equals MC delta T, which means we need to know the mass of the water. That's not the mass of the solid. So therefore, I would have to actually work out some way either to weigh the water or more likely use a measuring cylinder and then just do 1 gram, 1 centimeter cubed. And then if you've got a change, then I need to measure initial plus final temperatures. That's something that, again, a lot of people just say take the temperature and they forget about that initial temperature. So it's almost like you've got to imagine you were going to do the calculation and work backwards from there. So where it says explain how your results could be used to calculate the enthalpy of solution, it's almost really like you know how to calculate enthalpy change. How do you use that calculation to work out what you would do in the practical? Because you've probably done more practice of calculating enthalpy changes than you have of actually measuring them. It does indeed mean enthalpy change of solution. Yeah, they just get called slightly different things. It could also just be delta H, the solution. So I'd need to know, I'd need to use a sensible amount of water, and that's my other point about improving your practical confidence. This is a quick, easy tip that will help you write more sensible answers to practical questions. Next time you're in the lab in school, or just in the kitchen, to be fair, this also works in the kitchen, depends on whether your parents get annoyed with you getting in the way. Or in a shop, also works in a shop, but don't steal anything. Just get an idea for how big things are, okay? Get an idea for what 100 milliliters or centimeters cubed looks like. What does 500 centimeter cubed look like? What does 10 or 20 or 15? When you're in the lab, actually pay attention to what you're measuring out and what sort of containers you're using. Because like in titrations, they're always the same, 250 and 100 for the flasks, and then like 10 and 25 for the pipettes. Beakers are usually about 250 mils. So just kind of that sense of understanding is so helpful. And just in general life, just start to become a quiet little geek. You don't have to tell anyone about it. When you eat or drink something, just have a look at the packet and go, oh, that's 25 grams. That's what 25 grams feels like. Okay. Get an idea. Or what volume does that take up? Oh, that's like a little bottle and it's like 250 mils. So you know what it looks like. Because otherwise, my goodness, the calculation answers that come out. I've had students tell me that a packet of crisps contains 0.2 centimeter cubed of air. And I want to know where those crisps came from because they sound like they've got a lot of crisps or they're just really small packets. I don't know. But yeah, it just allows you to send, because sometimes you're going to have to suggest amounts and there will be a range that they will allow. But if, for example, I said I was going to add a liter of water, that would be crazy to this experiment because it would be so much water that it wouldn't get hot enough to measure anything. you'd want a small amount, 50, 100 centimeter cube max, because otherwise you don't get a lot of answers out. Okay. Last kind of, I did say periodicity comes up a lot. So first ionization energies, this was the worst first ionization energy question I think I've ever seen. In terms of, well, I don't mind it because, you know, it's fine. But I think for students, what we expect is to be told the pattern, or given a pattern, given a graph, given some numbers in a table, and then asked to explain them. Or occasionally, we might be asked to predict one thing, like, you know, predict the difference between like magnesium and aluminium, for example. And then we can just look at a periodic table and go, okay, yep, I've seen that one before. This one is worse because it's just a whole 8 elements, left to right, just a whole period. So, and explain means you've got to describe it as well. Okay, so this question didn't come with any graph or picture or anything. So how I would structure that, I wouldn't go from one element to the next individually. I would do it like you learn it, which is that there's a general increase across the period, and explain why. And any increase in ionization energy, in first ionization energy, is due to increasing nuclear charge. That is the only reason that first ionization energy across a period will increase, because all the other stuff that happens causes it to decrease despite the fact that there's more protons in the nucleus. When you talk, this is also a good strategy for lots of comparison questions, is when you talk about what changes. So I've said that across the period, the nuclear charge increases. So that's something different. Each element has one more proton. Don't then ignore what stays the same. Because if I go down the group, I've got more protons as well, but ionization energy doesn't increase then. So to be really clear, I would say that it's the same shells, same number of shells, so the same shielding. And so the outer electron is more attracted to the nucleus. And more energy to remove it. So structure, logical, and I've got like the main trend, because everything else is more likely the stuff that I'm going to make the mistakes on, to be honest, because that is where our language gets a bit wrong and funny. So then if I'm talking, I then just sort of look at the periodic table and go, right, where are the differences? My differences are between group 2 and group 3, so they're always in the same place. So I would say there's a decrease from beryllium to boron. So boron is lower than beryllium. And that is because boron's outer, or the electron, the best way to say it actually is the electron removed from, and then always then compare the two things. So electron removed from B is in the 2p, and from BE is in 2s. So I have this weird thing with my PowerPoint where it doesn't believe I ever want to write in the bottom left-hand corner and deletes it immediately. And so, and then you would say 2p is higher in energy. So less energy to remove it because it's already further from the nucleus. Further from the nucleus is the same as higher in energy. It's higher in energy, just is slightly better when you're talking about actual energy changes. I can then carry on and just say, okay, decrease. The next decrease is between nitrogen and oxygen. So there's actually only 3 things to talk about in this question. There's the general trend, there's the decrease from S to P, and then there is also a decrease from N to O. Phrase it the same way, electron removed, oops, from the same place in both chymes, so 2P, but nitrogen is 2P. 3, oxygen is 2P4, and I'm running out of space, but we would then say that the electron in oxygen is paired in an orbital. There's a bit of extra repulsion, which makes it easier to remove. So it's only really asking about 3 things, the general trend, and these come up over and over and over again. So being honest, no matter whether you're year 12 or year 13, you have done about ionization energies, unless you're doing OCRB maybe, in which case you might have not have done it yet. However, who finds that kind of question quite daunting and would just leave it? Or maybe just write a really short, give me a thumbs up if you think genuinely you would probably just go, nah, I'm not gonna do that. There's no way I could describe a whole pattern without anything to go on. Like, it's just too biology, the kind of thing they put at the end of the biology paper 3 or something. So yes, it is daunting, and it's going to be daunting if the first time you see it is when you start doing practice papers, or the first time that you practice this skill is when you're doing practice papers. And the problem is there's a lot of scary things in practice papers. They're not very nice. And you probably wouldn't only start doing really big calculation questions from practice papers. You've probably had lots of practice doing big calculations from past exam questions and things like that. And it's easy to just spot them because every calculations based topic, like acid base equilibria and all of that kind of thing, they in their practice questions will have big chunks of like long mark questions. But sometimes you just want to practice the skill. But the other reason that this is scary is because we don't make our brains do it enough. Okay, so we don't make our brains start from 0 often enough. We're too many times when we're revising, and I say we because it's a human thing. It's not necessarily a student thing. It's a human thing to look for something that's easy and comforting, and to avoid the stuff that's not, the stuff that's daunting, scary, difficult, etc. But when it comes to practicing, there are some things that we can do just regularly that will really boost our skills. So one is retrieval practice, which just means practicing without our notes. So there's different ways we can do it. We can do multiple choice questions. We can do quick quizzes. If you're on my mailing list, you need to be getting on those quizzes that I send out every single week. Yes, that's a really good question. Losing marks due to the exam stress and that kind of thing. Yeah, I still say that regular retrieval practice and just regular gentle practice within that area where it doesn't matter if you get it wrong. And that is the whole point of retrieval practice. There will be lots of things when I send out weekly quizzes that you'll have completely forgotten because that's in our nature. The whole point is you completely forget in a space where you can then go, right, I better do something about that, as opposed to completely forgetting on the day of the exam. And I've worked with loads of students with anxiety, exam stress, myself included. I got taken out of my second year of uni with chest pains from my exams. I was not a very chilled out student, but practice is really practice and small exposure to these things is what gives us more confidence. And it also means that if we're just having a bad day, that when I'm really tired and I've had a migraine all week, and I can still just about like teach some quite hard stuff because I've practiced it so much. So there are things that you can just do, even if you're having the worst day and you've got cold or really bad hay fever in the case of the summer exams, because you're just going to build that muscle and actually just do the best you can. The other thing is the weekly quizzes are in my mailing list. So yeah, just make sure that you are subscribed, and I will send out a little, if you ticked on my Google form that you wanted to receive it, you'll receive it anyway. So I will say that in a second. But the other thing is, you don't even need they're also on my website as well. You can find them. You just don't get them kind of quite as fresh as you do. And it's good to have the reminder by the email. Brain dumps. Get a piece of blank paper or a online whiteboard, or however you want to do it, or actually mini whiteboards, also very good. And literally just try, for example, the ionization energy topic. Try to draw that graph by memory. Try to explain what's going on. The drawing helps because it's easier than just trying to write everything out. When you've done a practical, that kind of thing, just actually try and write it out. We don't do enough writing anymore, modern society. So that's another thing that you need to actually practice. So definitions come up really often in 6 markers. So there'll be a 6-mark question, but at least 2 of the marks will actually be for a definition and maybe writing an equation to show what the definition means. So, and if you know the definition, you can really, really like pick up loads and loads of marks, and even not in the 6 markers, they're going to be there. The enthalpy change definitions, that kind of thing. When you practice definitions, again, practice them hard. Do not look at the front of a flashcard that says enthalpy change of formation and just go, yeah, I think I know that. Or skip over it in your head. Like you skip over it, you say it to yourself, you turn it over and you're like, yeah, that's what I said. Nailed it. Well, instead of actually getting that whiteboard and writing it down and then flipping it over and go, oh, I missed out the word mole, or I missed out standard states, because your brain will trick you. Again, all our brains are lazy. They don't want to do the work. So they will be like, yeah, no, we know that. So you have to test yourself to see whether you know it. There's not as much time at A level for your teacher to keep testing you, even though it might feel like they do all the time. And use your practical books, guides, whatever you've got that goes with the practical work that you do. I know that practical work can feel like a good switch off, but try to switch on maybe just even afterwards. Think, could I actually describe that method? If that was a core practical, I'd probably have to. Could I actually explain what I just did and why I did it? Just asking yourself that halfway through a practical is quite helpful if your teacher's not doing it. And it might just be because you've got lots of students or one of them's being a bit of an idiot and they're not a bit of glassware is not working properly. They might not be able to come around and directly ask you what's going on. So ask yourself what is going on. And if you're not sure, ask your teacher when they've fixed the glassware. So, yeah, I think I've kind of laboured the point. Practice is really important. My retrieval practice quizzes are free. I've also spent ages putting together a practice booklet for these kind of questions. So there are 20 questions in it. And they're all at least 6 marks, and some of them are 8, just because I thought, oh, they're really juicy and they needed a few more marks. And you can see they're in a real range of different topics. They are really probably focused towards year 13, actually, because there are some things towards the end. The first half, actually, the first 10, 11, probably the first 13 actually are completely year 12. So actually they're majority from year 12 content because that's where they tend to fall. So you have the questions, obviously that's not very helpful. What I really wanted with this, these are original questions. So I write practice papers and predicted papers and things like that. So I'm used to writing a lot of different questions and I've done a lot of exam marking as well. So they are not things that I've just grabbed from the internet and put together. They are things that I have obviously used inspiration for, but written myself. But then because the ones that you get from exams, the mark schemes are obviously aimed at examiners and they're really complicated. What I've tried to do is for every single one of those 20 questions, you have got like a model answer. So like this would be like the top student response or chemistry teacher response to this question with good structures and explanations. Then you've got an idea of how to get into each mark band. So, what you had to have in your answer to get 1 or 2 marks, what you had to get to 3 or 4, what you had to get 5 or 6, which is kind of what you would get in a mark scheme. A little box of keywords, so useful for like, oh, I couldn't do that. I need to learn those again, get those definitions down. And then also just like lots of a little box of tips and, how to approach this, what to watch out for, what students tend to get wrong most often on this kind of question, or what they miss out, that kind of thing. So that's a little booklet I've put together. It's $2.99 because I decided I spent so long on it that I am going to charge for this one. But it will be included in my half-term discount, which I was going to also tell you about. So yes, most of you are on this, I believe. If you're not, just make sure you are. If you go to my website, ckchemistry.co.uk, at any point, the little thing, annoying thing, I'm afraid, will pop up and ask you anyway. So just say yes. It will still pop up, sorry, but that's the nature of pop-ups. It's different for year 12s, year 13s, and tutors and teachers. Don't think if you sign up for the teacher one that you're going to get anything special. You'll probably just miss out on stuff, to be honest. I don't share special answers with them or anything. You get the weekly retrieval quiz. And if you are signed up for that on that list, then from Wednesday, I'm just going to have 24% off anything that's payable on my website. Anything that's online course or download. So that's practice questions for AQA and practice papers, sorry. So full paper 1, paper 2, paper 3, AQR and OCRA. And then there is my calculations online course, which I'm about to talk about. And then there's also my masterclasses, and then there's also that booklet. So it was meant to be starting today. Just like I said, been really ill for the last week, so I'm a bit behind on putting things up on the website. Also, a few of you have already been in my live group classes, which started, past tense, that image is a bit out of date, on the 13th of November for year 13, which means there's been loads of them so far. However, they've all been recorded, which means that there are a few spaces on the live lessons. There aren't many. So there are slightly more spaces on year 12. Year 12 is for any exam board, and it's exactly this time, Mondays at 5:30. For year 13, it's split up into exam board, AQA and OCRA. I'm sorry I don't do a specific Excel one at the moment. But that is AQA is on a Monday at 6:30 and OCRA is on a Thursday at 6:10. There are like a few spaces on each of those classes, but not many. But you can also get recordings access, which is super cheap. It's like for the year 13s, 50 quid will get you 19 lessons, which includes like topic checklist, practice questions, and the full recording of the class. That's a total amount. That's not per class. That is like, yeah, very, very cheap. And then finally, some people were asking about calculations and saying, what do we do about longer calculation questions? Because I didn't go over those. I am planning to do some more free classes related to calculations. There's one that you can already look at that I did in November. But I do also have this incredibly detailed online course, which basically goes through all of those topics in a lot of detail. So and if you look at the bottom, as you build through, because it kind of builds you through all the different types of mole calculations, the last topic is long answer problems with walkthroughs. So there are long answer problems with video walkthroughs explaining every single thing of it step by step after you've gone through all the others, which also have, so for example, if I took one of these topics, reacting mass percentage shield, within that, you have got 4 different videos explaining each different concept. So it's broken down, so we're not trying to overload too much. Practice questions, they've all got answers, and then you can see that the harder practice questions have got video walkthroughs as well. So anything where I think the mark scheme's not enough has a little video explaining what's going on. That's normally $49.99, but it's going to be 24% off for the rest of the week from Wednesday onwards. So keep an eye on the discount and just make sure you're on my mailing list, because if you don't want something now, you might want something closer to your exams. And I will be doing other 3 classes as well. So I do try to do more group classes and free stuff so I can get to more students and help them. Just if you've got any questions about anything, that's my email, claire@ckchemistry.co.uk. If you're on any of those socials, please follow me. I don't have many subscribers or followers because I'm not very good at social media. So if I'm kind of finished with my spiel, if you've got any more questions, please do ask, because I'm happy to go back and look at something, or otherwise I'm done. And there will be keep an eye on your inbox. Any tips on how to gain as many maths marks as possible? I do, and I reckon that definitely practice. If you didn't watch my class that I did in November, I'm pretty sure you can just find it on my YouTube channel. That was about calculations from experiments specifically. But I mean, I do, obviously, I feel bad because I just feel like I'm selling something. But I do recommend the course because it has like everything broken down. And from Wednesday, it's only going to cost £38 for an 8-module online course, which just has so many different practice questions and then builds you up. Because I feel like if you're doing lots of questionable things, it's because you're starting at too high and detailed a level and not just getting the other stuff, the foundations, sorted first. And that is my main tip for the maths marks, is get the foundation sorted, get yourself really clear on all your mole equations, and then look at every question as, what can I work out? How many things can I work out? Like, oh, I've got a mass, quickly do a mole, that kind of thing. Hopefully that was helpful. Right, okay. Unless there's any more questions, I will stop the recording there.